All right, last but not least, some of the practical application of these derivatives. Derivatives are actually quite useful in economics. So those of you taking micro and macroeconomics, these marginal costs and marginal revenues have a ton of application with derivatives. So it says in engineering you use velocity and acceleration to describe motions, but economists use rates of change with marginals. So if C of X is our cost of production, where X is the number of units produced, then the marginal cost would be dC dx, or C prime of X is another way if you want to write that note to yourself if you're more comfortable with that notation. So in example 5, it says, suppose it costs this many dollars to produce X radiators when 8 to 10 radiators are produced. And that R of X gives us the revenue from selling those X radiators. Your shop currently produces 10 radiators a day, so we're in this nice little sweet spot here. They want us to find marginal cost and marginal revenue. So to do both of those, it's simply the derivative. When you see marginal, it means the slope or the average rate of change of cost. Sorry, not average, instantaneous rate of change of cost at 10 radiators. So our first one is the change in cost, dC dx. So we can just use our power rule here, bring the 3 down, so we get 3x squared. Bring the 2 down, minus 12x plus 15. And then they want to know at 10. So if we plug in 10, we get, give me a second, should get $195. We do the same thing with the revenue, so change in revenue, marginal revenue. Bring the exponent down. Bring the exponent down. And again at 10. So you get a total of $252. Always important to have a bigger change in your revenue than in your cost. That's exciting. All right. Last but not least, the particle moves along a line so that its position at any time is given by the function S of t, remembering S stands for displacement. Where S is measured in meters and t is measured in seconds. That's going to matter because units matter on all of these questions. Always include the units. So it says, find the displacement of the particle during the first 2 seconds. Now, that's a key word. It's not saying at time 2. If it was just at time 2, we would just plug in 2 and figure it out. But this says during the first 2 seconds. That means I want to know from the time I started till the time I finished at 2 seconds. So here I'm looking for S of 2 minus S of 0. I want to figure out how far it traveled from the initial time till now. So if we plug in 2, we get 2 squared minus 4 times 2 plus 3. So 4 minus 8 plus 3. So we get negative 1 minus, what happens when we plug in 0? 0 minus 0 plus 3. So negative 1 minus 3 is negative 4 meters. Now, negative 4 meters, this is a displacement. It's not a distance, it's a displacement. So if our displacement is negative, it just means it either went backward or to the left. So then in part B, it says, find the average velocity. There's that key word, average. Average, we think algebra 1. Algebra 1 slope. And again, it says during the first 4 seconds. So that means I need 2 ordered pairs. If I'm doing average velocity, we're doing algebra 1 slope. So I want to start at time 0 and end at time 4. We already figured out s of 0. If you plug in 0, you got 3. And if we plug in 4, we get 16 minus 16 plus 3. So if we do average rate of change, y2 minus y1 over x2 minus x1, 0 over 4, which is 0, and then our units, we're doing a rate of change, meters per second. So instantaneous velocity at time 4, that implies calculus, which means we have to do the derivative. Instantaneous means derivative. So now I'm looking for what is v of 4. And that's the same thing as s prime of 4. So our derivative is 2t minus 4. And so we have to plug in the 4. So 2 times 4 minus 4. And we get 8 minus 4 is 4 meters per second. And then last but not least, acceleration at time 4. So acceleration is the same thing as v prime of 4 or s double prime of 4. So I'm going to go ahead and just use this velocity equation up here, and I'm going to find the derivative of velocity. So the derivative here is 2. And then our units, we've now done this derivative process twice, so it is meters per second squared.